Good morning, everyone.
Good morning, sir.
Good morning, sir.
Today is the first lecture of this second semester course that is on advanced concept in steel technology. So, before moving into this particular subject, let me tell you about the background of this particular subject. That means, at the end of this subject, what you are going to get from this, what kind of knowledge you are going to get this from this subject. Right? So, see here, basically. We'll discuss about steels, we'll discuss about different type of steels. We'll discuss about the microstructures of steels, because you understand that means if you're talking about microstructures of steels, that means different microstructures have different properties, right? That is called structure property correlation. Because if we change the microstructure in a steel, we can change the property of the steel, right? So we'll deal with that things also. And also we can see some how to change the microstructure in steel, some methods. And in this subject also you will be linked with some steel making processes, some advanced steel making processes. And also you will study some testing on steel, so important mechanical testing on steel, like tensile testing, impact testing and all. So overally, this topic is full of steel, introduction to steels, properties of steels, and how to make steels, and finally how to do testing on steels. This is all about this advanced concept in steel technology. This course is very well designed. Obviously, I think you will get benefit of this from this course. You will get benefit at the end of this course. Okay, so today is the lecture number one, and in the lecture number one will is the introduction to subject and steel. Okay, so here we'll discuss about these contents. One is steel definition, steel classification, and their basis of classification, and we'll discuss about microstructural evolution on equilibrium cooling from austenitizing temperature to room temperature, basically. And we'll discuss some properties of carbon steel. So these are the today's menu. Okay, so now okay, steel definition. So you all of you know, I think in undergraduate you well aware of that, what is a steel basically. See, steel is an alloy, right? Steel is an alloy of iron and carbon, basically. It is an alloy of iron and carbon, basically. But sometimes it is an alloy of iron, a very little amount of carbon, and other alloying element. So many times people make a mistake that if somebody asks what is a steel, people say steel is an alloy of iron and carbon. But that is wrong. Steel is an alloy of iron and carbon. That is fine. But steel may be an alloy of iron, a little amount of carbon, and other alloying elements may be there. Right. So that is steel. And steel is an alloy. Steel is not a pure metal, right? And measure or the base metal in an alloy, that is basically steel, is iron. So iron is the main constituents or main element which is present in the steel. And apart from iron, we have some alloying elements. That alloying element can be carbon, or it can be addition to carbon. Some chromium will be there, some nickel will be there, some tungsten will be there, some molybdenum will be there, some nickel, aluminium, some copper, manganese, many metals may be there, right, as an alloying element. But the major constraint is the iron here, right? So now you can see these are some cartoon diagrams. You can see here iron is there, iron atoms which are very big in size, very larger in size, and the carbon atom which are very small in size as compared to that of iron. So basically carbon is occupying the interstitial positions, or you can call This says voids, voids in the lattice, octahedral voids in the lattice of iron, because iron is a crystalline material, right? So once it is a crystalline materials, that means the atoms will arranged in a ordered fashion in 3 dimension, or there will be a regular periodic arrangement of atoms will be there in 3 dimension. And due to that kind of arrangements, we are having some voids, right? So that voids will be occupied by carbon. When you add carbon into iron and it will form an alloy of iron and carbon, you can call it as steel, right? Similarly, if you add some different alloying elements compared in addition to carbon, like chromium and nickel, for example, in stainless steel, right? So there is also that is also a steel. That is an alloy steel. Okay. So this is about the definition. So now you can also define steel on the basis of this iron carbon system, or iron carbon phase diagram, or you can say iron cementite metastable phase diagram, right? So if you look into, this is an iron carbon phase diagram, or I have written iron carbon equilibrium diagram, right? Same, all are same thing. Equilibrium diagram, phase diagram, both are same thing, because this phase diagram always formed due to equilibrium cooling of a liquid metal or liquid alloy to the room temperature. Equilibrium cooling means very slow rate of cooling. That is equilibrium cooling. Hmm. So here you can see, if you look, this is an iron carbon diagram. Here is temperature axis is there. In y-axis the temperature in degree centigrade, and here composition is there. Here the composition is weight in weight percentage, weight percentage of carbon, right? Temperature in degree centigrade and weight percentage of carbon. So it is 100% iron, but here it is not 100% iron. It is up to 6.67 weight percentage of carbon, right? Technically it should have 100% carbon, but we are taking 6.67 weight percentage of carbon in this end. But here it is 100% iron. So that means it is 0% carbon, and carbon percentage is increasing in this direction, and finally it reach up to 6.67. So you can see here it is written steel. Steel means up to 2 weight percent here. Some books may written 2.1, 2.03, 2.8, like that, but you consider 2%. That means starting from a minimum carbon value to 2 weight percentage of carbon in iron or in iron carbon alloy is called steel. But if the carbon weight percentage is above 2 weight percentage, it become cast iron. So steel and cast iron both are alloy of iron and carbon, simply. I hope you people have well understood up to this. So in this way, you can define steels. Now, steel classification and their basis of classification. So we can have some thousand number of steels available, more than thousand number of steels. Various grade of steels are available. Maybe in sometimes we'll discuss that, how to identify a particular grade of steel. We can discuss that in coming lectures, but today we are not going to concentrate on that topic. But today we'll classify the steel on a general basis. So steel classification and their basis. So steel classification, we can classify steel like this. If you look at here, the basis of classification steel types. One is alloying element governing the property of steel. So this is one of the way you can classify the steel. Alloying element governing the property of the steel. See, in a steel, the primary alloying element may be carbon, or the primary alloying element can be some other alloying element, basically some substitutional alloying element. But carbon here is a interstitial alloying element, right? So if carbon is the principal alloying element present in the steel, that means only iron and carbon is there. No other alloying elements are present, or even if some other alloying elements are present, their concentration is very low, then we can call it as plain carbon steel. Plain carbon steel means carbon here is the major alloying element. Why major alloying element? Because the property of the plain carbon steel will be decided by the weight percentage of carbon present in it. It is not decided by the other alloying elements. That means the concentration of other alloying element will be very negligible, or it may be absent completely. Right? So that is plain carbon steel. So plain carbon steel is an alloy of iron and carbon basically, right? And the properties is governed by the weight percentage of carbon. If the weight percentage of carbon will change, the properties will change. I'm talking about basically mechanical properties, maybe hardness, maybe strength, maybe toughness, maybe ductility, maybe wear resistance, right? These are some properties, basic properties. Second one, uh, on the basis of carbon weight percentage. So that means you can understand if I'm talking about carbon weight percentage classification, that means on the basis of how much weight percentage of carbon present in steel, that is basically plain carbon steel. So we can classify plain carbon steel into low carbon steel, medium carbon steel, and high carbon steel. This is one of the way. That is on depend on weight percentage of carbon in plain carbon steel. So low carbon steel basically it means what? For plain carbon steel, the weight percentage of carbon is below zero point 0.3. If the weight percentage of carbon is below zero point 0.3, it is plain carbon, low carbon steel. So what about medium carbon steel? So medium carbon steel means the weight percentage of carbon, is below, or sorry, is in between, or is in between point above 0.3 to 0.68 percentage. This is the range. In this range, 0.3 to 0.68 percentage range is medium carbon steel. And you understand if it is a high carbon steel, then weight percentage of carbon will be above zero point 0.6. Weight percentage of carbon above 0.6. Right? So this is the way. Some textbook might have written 0.35 like that. So you should not be confused. It is fine. 0.35 to 0.65. Here above 0.65. So if you are taking 0.3, that is fine, no problem. If you are taking 0.6, that is no problem. If you are taking 0.6, that is no problem. So this is the way of classifying plain carbon steel: low carbon, medium carbon, and high carbon. There is another way of classifying this plain carbon steel, again on the basis of microstructure evolution on equilibrium cooling from austenitizing temperature. This is very interesting. You people have a good idea on this, I know, but still I would like to discuss here. Because the properties of steel depends upon the microstructure, that's why. So microstructure evolution. So here equilibrium cooling means, you should understand, equilibrium cooling means very slow rate of cooling. But here it is written from austenitizing temperature. From austenitizing temperature means initial temperature is that temperature where 100% austenitic grain will be present. That may be above A1. A1 temperature means lower critical temperature. So A1 temperature above is austenitizing temperature for eutectoid steel, when the weight percentage of carbon is 0.8 weight percentage. But for low carbon steels, below that weight percentage of carbon is, that is above A3. Some people write AE3 also, if E represent equilibrium. That is upper critical temperature. Similarly, if the carbon percentage is above 0.8, the austenitizing temperature will start from above ACM. CM represents cementite basically. Or some people write AECM. AE means equilibrium. Right? So I'll show you here. So on that basis, we can have hypoeutectoid steel, and hypereutectoid steel. Right? So hypoeutectoid steel means the steel containing carbon percentage below 0.8 weight percentage. That is hypoeutectoid steel. Here you can see that. It is also written over here. This up to minimum 0.025 to, oh sorry, 0.008 weight percentage to up to 0.8 weight percentage. Or in some textbook, they have written 0.77 weight percentage. This is a hypoeutectoid steel. Then that is, what is eutectoid steel? At this composition. Here it is written 0.76, but it is written wrong somewhat. But basically it is taken at 0.8 or 0.77. Right? So if the weight percentage of carbon is only 0.8 weight percent or 0.77 weight percent, that is eutectoid steel. So again, when the carbon percentage is above 0.8 up to 2.8 percentage, that is hypereutectoid steel. So this is the another way of classifying. So now I will show you the microstructure evolution on equilibrium cooling from austenitizing temperature. This is very interesting. Just look at this diagram. The microstructure evolution in hypoeutectoid steel. As I told, hypoeutectoid steel is that steel which contain weight percentage of carbon below 0.8 or below 0.77, right? So how the microstructure will evolve when we have steel at high temperature, that is austenitizing temperature. Finally, we are cooling at a very slow rate to the room temperature here. So you can see that means this is 0. You can understand this is one of the important part of the iron carbon phase diagram, right? This is the temperature axis, this is the weight percentage of carbon axis, right? And this part is showing what? This is your ferrite or alpha ferrite or alpha, this part. And this part is the alpha plus austenite. This part is austenite. This part and this part is austenite plus cementite. And this part is ferrite plus perlite, and this part is perlite plus cementite. Right? This is the these are the different phase and mixture of phase present. So now you can see here. Suppose our starting temperature is this one. So this temperature means this is a single phase region, that is austenite, right? Single phase austenite is a single phase region. So this is a high temperature. So we'll start from here only. So that means you can see how the microstructure looks like. Austenite is a solid phase. All these phases are solid phases, right? So these are the austenitic grains. Austenitic grains are basically bigger size grains. You can see individual grain of austenite. It is a single phase. So in once you are looking at the single phase microstructure under a microscope, you can able to see only grain and grain boundaries. Nothing else will be appear because it is a single phase. Single phase means there is 100% solid solubility is there, right? Even if carbon is present, that carbon is completely soluble in this austenitic grains, right? So now we are slowly decreasing the temperature like this, but we are reaching at this temperature, just below this temperature. This is your A3 line or AE3, upper critical temperature, right? This is your upper critical temperature. This is your ACM, again upper critical temperature. And this one is your lower critical temperature. That is A1 or AE1. This one is the AE1 or A1. E represent equilibrium. You can write A1 or A1. No, there is no problem. This temperature is also called eutectoid temperature because eutectoid transformation happens at this temperature, right? This is upper critical temperature. This is also upper critical temperature, but this upper critical temperature is name is A3 or AE3. But this one is ACM, and this one is A1 or AE1, lower critical temperature, right? Now that means, and you remember, you can look at this one also if you want. If you remember, critical temperature means at that temperature where the phase transformation happens. Phase transformation happens means here your crystal structure will change from one crystal structure will change to another form of crystal structure, right? Or you can say one phase will be transformed into another phase because one phase have one particular crystal structure, another phase have another particular crystal structure. You understand? So you can see where, okay, this one. We are decreasing the temperature from here. So now we have one phase, that is austenite. The crystal structure of austenite is FCC, you understand, phase centered cubic structure, or closed pack structure, CCP. Now we are decreasing the temperature slowly, slowly, of the steel. Now we reach the temperature just below this one. That means at this temperature, phase transformation will start, because this is an upper critical temperature. Critical temperature. So here phase transformation start. So you can see what is the phase available here. Two phase region. This is a two phase region. One is austenite and one is ferrite, because here austenite is present, here ferrite is present. So here it will be austenite plus ferrite. So that means some of the austenite will be transformed into ferrite, right? Some of the austenite will transform into ferrite. All the austenite will not transform into ferrite. You understand? So that means, and you understand, when a new phase nucleates, because phase transformation will happen by two methods. One is the nucleation stage, and the one is the growth stage. That means a new phase will start nucleating at high energy regions. And we understand high energy regions are the grain boundary regions, right? So here we have grain boundaries of austenite. So along the grain boundary of austenite, the new phase will nucleate, right? So that is which new phase? You can see ferrite will start nucleating. So you can see these are the ferrite, but here it is representing nucleation and some growth also. Some growth has happened. Hmm. A small nuclei of ferrite will nucleate at the grain boundary of austenite, and it will grow, and it will grow along the grain boundaries. That is the thing. So finally, when you can see this is the growth has happened. This picture is showing the growth has happened. That means some of the part of the microstructure has become ferrite, and other part is austenite, right? But now the point is what, when we go down this lower critical temperature, this portion, this temperature is just below the lower critical temperature. So again, this is a critical temperature. Critical temperature means phase transformation will complete now, or will happen. So that means the rest of the austenite which do not have transformed into ferrite, they will start transforming into perlite, right? So you can see this is a microstructure here. So that means these white grains are ferrite grains, and this alternate layer kind of grains are perlitic grains, right? Let me expand it if you want. It will be more clearly visible. So this shaded portions are perlite, and these white portions are ferrite. So this ferrite is actually called pro-eutectoid ferrite, right? So this ferrite will not undergo any kind of transformation. Transformations always happen from austenite. You should remember that, right? Austenite is the parent phase always. So from the parent phase, transformation will happen, right? So since some of the austenite has transformed into ferrite, so no transformation will happen from ferrite. Only the rest of the austenite which has not undergone transformation will transform into perlite. So at the end of this cooling, equilibrium cooling of this hypoeutectoid steel, you will be getting what? You will be getting pro-eutectoid ferrite plus perlite. And pro-eutectoid ferrite is a soft phase, and perlite is a hard phase. Hard phase means it is a stronger phase as compared to ferrite. Ferrite is a very soft, ductile, but the perlite is having high strength basically, and good toughness also. And if you have confusion about this microstructure is just showing, if you start from if you start from here if you start from here, this is a ferritic region, only ferrite, right? Or if you start from here, for example, so here you have austenite will transform into ferrite only, and this ferrite will be cooling down to finally get to ferritic grains. Ferritic grains are also, ferrite is a single phase region microstructure, means only grain and grain boundaries, nothing else will be seen, right? Here you can see grain and grain boundaries, but different, sometimes in interview they ask what is, how you can distinguish austenite and ferrite, because if you look at austenite, you'll find only grain and grain boundaries. If you look into ferrite, you can able to see only grain and grain boundaries. But what is the difference? Recently, the BTech student has been asked this kind of question: how to differentiate ferrite and austenite? The difference is what? The grain in the austenite are bigger, but the grain in ferrite are smaller, right? Suppose I will take a temperature here. So I will have a big size austenite. But if I will take a temperature here, our starting temperature is here, I will get a small austenitic grains. But even if that is a small austenitic grain, but that grain size is bigger as compared to ferritic grains. So I'll move on to the next microstructure evolution. When I will consider now, if I will consider now hypereutectoid steel. Hypereutectoid steel, as I told, this is the composition of hypereutectoid steel. I have taken 1.28% of carbon here, right? Hypereutectoid steel means the steel containing more than 0.8 weight percentage carbon. So it is 1.2, it is higher. So this is hypereutectoid steel. So I will start from here. This is the austenitizing region. You remember this is the upper critical temperature, that is ACM. This is ACM. ACM is the upper critical temperature, right? So here it is starting temperature. Starting temperature here it is austenite completely. Austenite means we have grain and grain boundaries of austenite. Fine. Now I'll slowly do equilibrium cooling. I'll do slowly cool down this steel. Now when I will reach this temperature, for example, this is the transformation temperature. What will happen? Some austenite will transform into cementite, not ferrite. Cementite. So you can see, but it is not clearly seen here. I will show you some another diagram. So what it means? Some of the austenite will transform into cementite. So what will happen? Basically, along the grain boundaries, the cementite will nucleate first. Small particle of cementite will nucleate. Slowly, when you move down this temperature, because you can understand this region is cementite plus austenite. The cementite will start growing along the grain boundaries and it will cover the grain boundaries. So it will form a network of cementite or cementite network along the grain boundaries. Finally, when I will reach the temperature below this temperature, this is the lower critical temperature. Again, phase transformation will start. So rest of the austenite which has not undergone transformation, they will transform into perlite, right? So finally, at the end of this cooling, we'll get a network of cementite along the grain boundaries. These are the network of cementites, white portions, and this shaded portion is the perlite. Fine. Now I will discuss about if we take eutectoid steel. Eutectoid steel means steel with 0.8 weight percentage of carbon or 0.77 weight percentage of carbon. Here, this one, right? So I will start with suppose here at this point. So at this point, this is what? Austenite phase. A single phase will be there like this. But if you go down this temperature, this is the lower critical temperature. So what will happen? This austenite will become unstable, and once it become unstable, it will transform into another phase. What kind of phase? Entire austenitic grain will be covered by perlite, which is basically ferrite plus cementite will be there. So perlite is not a phase. Perlite is a mixture of phase because it consists of two different phase. One is ferrite and one is cementite. Cementite means the weight percentage of carbon is 6.67. Ferrite means it is basically maximum weight percentage of carbon in ferrite is 0.025 weight percentage and minimum is 0.008. Uh, Now for better understanding, I'll show you same thing but in different way, different colorful diagrams, colorful cartoon diagrams. Just look at here. So this is eutectoid steel diagram. So that means upon equilibrium cooling, upon slow cooling of the steel from austenitizing temperature to the room temperature, I will get perlitic networks, perlitic colonies. These are colonies of perlite. The brown, this reddish orange color is your ferrite, and these are cementite, for example. Fine. But if you consider a hypoeutectoid steel, you can end up with this. You can see this is a very good diagram. You can see initially at high temperature, austenitizing temperature, we have austenitic grains, gamma, and this is the upper critical temperature, as I told, A3 or AE3. Just below that temperature, some austenitic grain has transformed into ferrite, which has nucleated along the grain boundaries. Finally, if you reduce the temperature, go down, this ferrite will grow along the grain boundaries. You can see, cover the grain boundaries like this. And finally, when you go below this temperature, this is the lower critical temperature, or eutectoid temperature, lower critical temperature, that is A1 or AE1. What happens? The rest of the austenitic grain will transform into perlite. So you can see we have proeutectoid ferrites along the grain boundaries kind of, and rest part is perlite. This is called proeutectoid alpha. So similarly, if you look at this diagram, this is for hypoeutectoid steel. At this temperature, we have complete austenite. That means this is the upper critical temperature, that is ACM. Hmm. We have austenitic grains. When we move below this temperature, some of the austenitic grains have transformed into cementite, which has nucleated along the grain boundaries. Slowly, if we take a temperature here, above this lower critical temperature, they have been grown along the grain boundaries. Then when you go below this temperature, lower critical temperature, or A1 or AE1, the rest of the austenite has transformed into perlite. So you can have a network of cementite along the grain boundaries, and inside them we have perlite. And you understand this is a very good reaction. The austenite transform into ferrite and cementite. This is which kind of reaction? This is eutectoid reactions. All are solid. This is solid, this is solid, this is solid. So this is a solid state phase transformation upon cooling. Some people write 723, some people write 727. Many textbooks have written 727. That means austenite has become unstable. Austenite is unstable below this temperature. That's why it is transformed into two different solid phases. Okay, so let me ask you a question. How you people decide what is the composition of this one, composition of this one, and composition of this one? By which method? Can you people tell me? Am I audible to everyone?
Yes, sir.
Okay, can you people answer me how you will decide the composition here? This is 0.8, this is 0.025, 0.6167. By which method? Everybody have gone through physical metallurgy class in undergraduate. Nobody is answering? Okay, anyways. So composition of individual phases will be given by tie line rule. Tie line. Tie line is a horizontal line drawn in a phase diagram. So suppose this is a phase iron carbon phase diagram. I will draw a tie line. Suppose here this is a tie line, for example. I will draw a tie line here. Because you can see this is suppose eutectoid composition 0.77 or 0.8. So so composition of steel is 0.8. So I will draw a tie line. So this is a tie line, for consider this is a tie line connecting all the phases. This phase is alpha, this phase is cementite, right? So here what is happening? Eutectoid reaction is happening. Here this is austenite gamma. Is when cooling upon along this temperature, it is transformed into alpha plus cementite. Because this is the alpha region, this is the cementite region. So entire region is alpha plus cementite. You understand? So gamma transform into alpha plus cementite. So how to decide the composition? Composition, see, this is gamma is a single phase. So once it is a single phase, that means the weight percentage of alloy is equal to weight percentage of the composition of the phase. The phase composition is equal to the weight percentage of the alloy. So alloy weight percentage is 0.8 weight percentage carbon. So composition of this single phase is also 0.8, right? But now it has transformed into gamma alpha plus cementite. So what is the composition of alpha? This is a tie line. Tie line is intersecting the alpha here. So this portion is, you should remember, that is 0.025 maximum solubility of carbon in alpha iron. That is 0.025. So it is written already 0.025. You can see 0.025. And we understand this tie line is intersecting this phase at here. And what is the composition here? It is 6.67, which is the cementite. So here it is, cementite is 6.67. Understand? So by drawing a tie line along the phase diagram, which is a horizontal line intersecting the phases, you can identify the composition of the particular phase. So composition of a particular phase can be determined by using tie line rule, which is a horizontal line in the phase diagram intersecting the different phases. And you have to remember, if it is a single phase always have a composition equal to that of the alloy composition, right? Because here gamma is a single phase. So alloy composition is 0.88% of carbon. So gamma composition is same 0.88%. But here this is a different phase, then this is a different phase. So the maximum weight percentage is the composition of here, and maximum composition weight percentage is the composition of this one. Okay, up to this, I think there is no doubt. So up to this, it is clear to everybody.
Yes, sir.
Okay, fine. So now, okay. So a question is like this: what are the different impurities, or what are the different alloying elements present in a steel, basically in common sense, in common way, or you can say impurities. So other impurities present in the steels are silicon, manganese, phosphorus, sulfur. So these are the impurities which cannot be avoided. They will be definitely present in the steel anyhow. So they are considered to be an impurities, basically. You can try to remove it more and more, but still they will remain. Hmm. Because we understand the activity or the chemical potential of a particular element decreases with the decreasing in their weight percentage. So once the chemical potential or activity of these alloying elements or these impurities is going down with their weight percentage, so they will become more stable, or they will become stable in that particular phase, or in that particular phase means steel. So it is very difficult to remove them, right? So now, these are the impurities. So you understand, it is written concentration must be below safe limit so that it will not affect the property of the steel. So even if silicon will be present, manganese will be present, phosphorus, sulfur will be present, some aluminum may be present, right? They should be present in a safe limit. The concentration should not be very high. Otherwise, they will affect the properties of the steel. Which kind of property? Basically, the mechanical properties like hardness, strength, ductility, toughness. They will get affected if their concentration is high, right? uh, as you people remember, what is the problem with phosphorus? The problem with phosphorus is what? Okay, phosphorus cause cold shortness in steel. So this is the way by which phosphorus is detrimental to the steel property. Cold shortness. And what about sulfur? Sulfur cause hot shortness in steel. So phosphorus cause cold shortness and sulfur cause hot shortness. If you remember in your thermodynamics and kinetics lecture, I have told you what is hot shortness and what happens when hot shortness occurs. So hot shortness basically seen at, it is seen during which process? Can you people tell me?
Rolling.
Hmm? Which kind of rolling? Hmm? Hot
Hot
working
rolling.
processes. Hot working or hot rolling, right? When the temperature is high. So do you people remember why during hot working or hot rolling processes this hot shortness effect is seen, not in low temperature process or room temperature processes? What is the reason?
At
Hmm?
high temperature, sulfur reacts with iron to form iron sulfide.
Mm,
Sir, at the time of rolling, the FES has low strength and low melting point, so it will break.
very good, very good,
Hot
very
roll.
good. Because if you remember, if you have high sulfur content in your steel, so sulfur will start reacting with iron, right? I'm talking about molten steel. So in the molten steel, you have iron and you have FeS, right? In the molten steel, you have iron and FeS. Why FeS? Because sulfur concentration is high. It start reacting with sulfur iron to form FeS. So you have Fe and FeS. But now you are doing solidification of it. The moment you are solidifying something from the molten state to the room temperature, right? So what will happen? That means one is Fe is high melting point substance, but FeS is low melting point substance. The melting point of FeS is nearly 910 or 917 between that. It is a eutectic compound. Presence of FeS, which is an eutectic compound. Eutectic compound means low melting point compound, easy melting point compound. The compound which melts at a low temperature. So what will happen if a if you are doing solidification of an particular substance containing high melting point substance and low melting point substance? At the end of the solidification, you'll be having a thin film of low melting point substance along the grain boundaries. Inside the grain, you have high melting point substance, right? So what will happen? That means you have a solid steel containing FeS along the grain boundaries. The concentration of FeS more is along the grain boundaries, but inside the grain, concentration of Fe is more. Now you are doing hot working, hot rolling. Hot working and hot rolling is carried out at a high temperature, that is above the recrystallization temperature. For the steel, recrystallization temperature is basically above 900 degrees centigrade. We do hot working above 900 degrees centigrade, like 1000 degree, 950, like that. So what will happen? Now what will happen? Along the grain boundaries, the FeS is present. It is a easy melting point substance, easy melting point compound. It will start melt, but Fe will not melt. Its melting point is very high. So what will happen? Along the grain boundary, melting will start. So what will happen? The grain will get separate from one another. So the mechanical properties getting deteriorate along the grain boundaries. It will lead to separation of grains. So finally, the material will get crack or it will get damaged completely. So that is called hot shortness. Okay, I think I will stop here and I will continue the lecture from the next class. If you have any doubt, you can ask me right now. Okay, I think there is no doubt. Or if you have any doubt, you can call me up.